Check, 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 check. Okay. Yeah. Okay, that's better, right? You can hear me clearly. Okay, perfect. Let's get started. All right. So I am back. I was actually sort of down with, um, I'm not pretty sure what it was, but some kind of a sickness. But that's over. I'm back. And this on this stream, we're going to sort of go through the, sort of complete the board bring up, because I think I have it working. So this is going to be a part 2 from, with respect to the last one. So the last one we discussed a couple of things. Let's just pull up our notes over here. So in the last one we looked at, obviously we've looked at the board quite a bit, because we started out with understanding JTAG and how the JTAG debugging port can be used to debug code that is written for, basically any of your embedded processors. And then we looked at, where do we start when we say, okay, this for this particular board that we're using, which put it up, ARMv8-A Nano. So this board, picture, it. Right. Picture is not back. Yeah, I presume this is visible. Yeah, let me just check the chat. Visible, right? Okay, yeah. So Yashwan's asking, can you sort of brush up a little bit on board bring up for 1? So that's exactly what I'm going to do. We'll sort of just go through the pieces that we learned, or rather we went through on the last session, and then we'll continue with today's piece. So yeah, this is the board that I've been using. This is our JTAG port, which is what I've been relying on to debug my code, because what I'm writing is startup code, which means we don't have access to something like a UART console, etc., because we haven't even, there's no way, the board is just starting up, and there's no code that you've actually written that gets to execute on that. So given that this is your only option, and now we're actually going to take a look at, we're going to take a look at JTAG debugging in a little more, with a little more hands-on stuff. We'll take a look at that. But this is the board. This is our, I don't know if you can see this. This is the processor, and then there's, I believe there's a Wi-Fi chip over here and all of that, which I think we've covered on the last time. Now, also in the last session, we went through the pieces that were required to get something working on the board. Things like, we write a startup code file, which is what this is. So I said, you actually wanted to look at the implementation, you could go to the rustBoot project and then jump into bootloaders. And then we have a separate folder now called the i.MX8MN. And then you can simply go ahead and look at folder, the source for that folder. Within that folder, you should be able to see the bootloader implementation itself. Now, I hope this is clearly visible. I hope the font is good. I take it it's good. Okay, yep, good. So I said there's 3 different files, or rather 3 different pieces that you sort of need to put together to get your board up and running. First one is obviously going to be the entry.s file, which I mentioned is the assembly component. So whenever you bring up a board, there's some amount of assembly that you will need to bootstrap the board. That's what we've put together in entry.s. And I went through a little bit of that, saying we start off when the board is booted and let's say the ROM code gets to run and it hands off control to your code. The very first instruction in your code is this one, because that's how I've written it. And we basically start off in the reset section and then we start our execution. And after that, I mentioned, you need a linker script, which is what this is. We went through what the linker script does, etc. We went through, how your program, that is your text section, your data section, your global offset table, your stack, all of that, how was it supposed to be exactly laid out in because we needed to define these things clearly so that, your code goes and sits there, your data section goes and sits there in memory, all of that stuff. So you need the linker script, you need the assembly file, which is your startup code, linker script, and then you need your main.rs, which is this. For now, the main.rs file is basically a bunch of print statements, but the last time when we actually looked at this, we couldn't get anything working because somewhere something was going wrong and we couldn't figure out what it was. So in this stream, what we're going to do is we're going to complete that. We're going to get basic UART functionality working, because once we get that, everything else is just, we don't need to rely on something as involved as JTAG debugging. You can pretty much go ahead and use the UART to do your debugging, printf style, right? Okay, any questions on this so far? Okay, right. Well, I guess not. So far, this is what we covered in the last session. In this session, what I wanted to actually go through was I've managed to spin up the VM, because I remember last time our VMs were not, there's some issue with the VM. I couldn't connect the device, etc. But now I think VM should be working properly. You should be able to see it right now. Can one of you confirm that you can see the VM? So basically, I spun up my virtual machine because I'm running, my main device is the Mac, and I had some issue trying to set up OpenOCD properly. More importantly, I needed to install a patch, apply a patch to OpenOCD, because I'll show you what I mean, why I needed that. But that was not possible on the Mac because whatever dependency con. So I went ahead and, sort of did this, and just booted up a VM, started working out of it. Okay. So now that we're in here, let's actually go through this step by step. So what I'm going to do right now is, first things first, I am going to spin up what is called OpenOCD. So this is the OpenOCD command. Basically, I say OpenOCD, and F is for use this file, which is particular script. So my debug probe is actually an FTDI probe. So the probe's basically the probe's description, or rather the probe's name is UM232H. Actually, it's called FT232H, but here it's named UM232H. That's fine. And then my Nano board also has its own configuration. So I need to supply two different configurations. One is a configuration for my probe. The other one is a configuration for the board that I am going to be using. And these are available as part of the, any installation of OpenOCD. You probably have them. Otherwise, you'll have to write them yourself, which is another thing in itself, which maybe we'll do a stream later on. But yeah, that's interesting as well, because you can actually go ahead and extend OpenOCD for things that you want, etc. But all that's different. We have it, so we're going to run with it. But before I do that, I figured out that in order for me to actually go ahead and enable the USB device, I needed to do this. So once I do this, now I should be able to turn on the device. Yep, and now you see it works. So previously when I was actually running this, you saw that it ended up throwing like non-existent errors or something like that. But now, once your device is powered on, that means my i.MX8 board is powered on, and I have got OpenOCD running, I should be able to see this. It's so basically it's figured out that there is a tap. I think we sort of discussed this, but let me just hash this out again. So my laptop is connected to a probe, the FTDI probe, and that probe is the one that's connected to the JTAG port on the device. This is the i.MX8 device, right? So you can go ahead and query that board using the probe is actually doing all the querying, and you're using the laptop to control the probe. All right, that's what you're trying to do. And over here, what's actually happening is when we say JTAG tap, tap is for it's basically debug access ports. In this case, it's a test access port is what you can call it. But essentially, it's a port that you've connected to, and you're looking for things of interest. And basically in this case, you're looking for things like, is this, I want to sort of connect to the CPU on this device, and I want you to help me debug it. All right. That's what's happening over here. The device was found, and there's a particular ID for it, and all of that. Okay. Anyway, we're not going to get into all of that. The important thing here is you have to keep in mind is that you have, these are hardware breakpoints and watch points. Okay. So whenever you sort of debug code, let's say normal web development code, etc., you normally apply breakpoints and stuff. Similarly, similarly in the embedded world, when you're actually debugging with something like a JTAG debugger, etc., you can apply hardware breakpoints. Now, these are things that are offered to you by the device itself. So without getting into a lot of detail, know that when I keep saying I have this JTAG port, I have this JTAG port, that JTAG port is actually connected to some debug infrastructure that is present on the chip that is actually provided by ARM itself. That is what is called the ARM debug standard, right? And part of that is it's got a bunch of debug registers, it's got a pinout count, it's got this breakpoint and watch point infrastructure, tracing stuff, a lot of that stuff. So basically the key point over here is that these breakpoints are, you're actually limited. These are actual hardware breakpoints wherein you can set 6 at any given point in time. And if you try to set another one, you probably have to remove the other one and then set another one. You only get 6. That's the key point I'm trying to make. And then you also have the option to start up a GDB server, etc. If you spin up your GDB client, which we're going to do right now, it can connect to the GDB server that this OpenOCD client is pulled up, or rather spun up. It's already running. All you have to do is connect to it. So in order to connect to it, I can simply go here. I can simply go here and I can say, because I've already done all of this, I'm like going to go through. Yeah. Oh, I sort of have to navigate to the right path because I'm in a VM. I've sort of put it somewhere. The Rust projects, and where was this? Oh. And yeah. Yep, so yeah. So this is my GDB. I just turned it on. Now what I do is I need to connect to the device. So as you saw, the GDB server is already up and running. OpenOCD instantiated it. It's there. All we need to do is connect to it. So I'm just going to go ahead and connect to it. Now I've connected to it. And if you see, this is actually an address that's, you know, somewhere in ROM code on the i.MX8. Right? So somewhere in the ROM code on the i.MX8, the execution is halted somewhere. We just landed over there because there's nothing more to do. I have not given it, like for example, I've not given it uboot or uboot, you know, the kernel or anything like that. Just said, you know, it's an empty device. I've just turned it on. So that's where we ended up. Now, the first thing I want to actually show you is, you know, when you're actually debugging, you can run, you know, with GDB, you can run your own commands. So I'm going to first things first, I'm going to reset the device. So when I reset the device, you will see that the device, you know, GDB. So the way it works is GDB, the client, you know, will make that request to the GDB server. The GDB server will pick that up, and then your command is actually going to be interpreted by OpenOCD, and OpenOCD is going to drive the probe, and the probe is going to, you know, basically query the debug port on the device. So that entire cycle happens whenever you try to whenever you try to run any command on GDB. That's exactly what's happening, right? So any questions on this so far? On the basic layout and things? Right. No questions? Okay, great. Okay, sorry, I missed. Okay, so let me move this better, right? Okay. I hope you can see the screen now. All right, so I hope everything is clear and nothing is sort of blocking. I actually see two artifacts here. Anyway, let me just first go through this. So now that we are at this point wherein we've just reset the board again, when I say mon reset halt, I basically mean monitor reset the the board and halt. Once you reset the board, halt. Clearly, now you see that there's a couple of things happening here. The first thing is that we're halted. Problem with the audio. You hear me? Okay, fine. Everything cool, right? Okay. So clearly, if you see this over here, you have yeah, what I was saying. Yeah, this particular line. When we do monitor reset halt, we basically say that reset the board and just halt after you've reset. So that's what's happened over here. It's reset the board, and notice that, you know, it's not actually looking at this particular board has a quad core processor, but we don't care about the other three because they've not been spun up. The only one that's been spun up is the first one, that's core 0, and it gives you right off the bat some information, which is this particular board, this particular core is halted. It's in the ARM 64-bit state, and then the current exception level is EL3, and then it gives you some registers and stuff like that. And it also says something very important, because this is the one that actually took up quite a bit of our time. For some reason, the MMU is enabled, and when the MMU is enabled and I was trying to jump to a particular address in memory, I was getting debug errors. Means basically the debugger in this case would not allow me to sort of jump to that point. So I had to go ahead and install a patch that will allow me to disable the MMU before I do the job. All right. That was the other thing that took up quite a bit of time. Anyway, and then the MMU is enabled, data cache is disabled, instruction cache is enabled, right? So you get a little bit of information here. The first thing I'm going to do is, as I said, I'm going to actually disable the MMU. In order to disable the MMU, by the way, this command, which is disable MMU, does not exist in your regular installation of OpenOCD. So you were to install OpenOCD right now on your system, be it Windows or Mac or Linux, you will not be able to find disable MMU as a command. You'll need that patch in order to install it on your system, right? So that's another part about debugging. You have to come up with custom solutions or problems. So anyway, now that's done. I've gone ahead and disabled it. Just to show you that I've disabled it, I'm going to go ahead and reset the board again. Now you see that the MMU is disabled. This part. So previously it was enabled. Now disabled. All right. So now that it's disabled, what I can do is when I actually spun up GDB, actually scroll to the top, you will see that I've already sort of provided GDB with my file that I'd like you to load. Whenever I want you to load, I'm going to give you the command, but I want you to go ahead and load this file, right? So, so if you see that, I'm just going to go ahead and load that particular file. I've gone ahead and loaded it. Now, a couple of things have already happened. I've already compiled that, you know, I've already compiled the whole file, the project, and the binary is now being sort of loaded into this address. That's hex 912000. And the size of my, you know, file, or rather my binary, is hex 5000 at this point. You know, that's kind of what's been loaded. So this is, you know, how you would simply go ahead and load a file load your binary directly onto the board, instead of, you know, sticking in an SD card or all of that stuff, which is normally what you do when you want to boot a system. But when you're starting off debugging, etc., you'd use the JTAG port to directly load in your code and start running and see what's working and what's not. The reason for that, this is much quicker as well, and this is how you debug. So now that that's in place, the first thing I'd like to do is I'd like to show you how what's working. So I'm going to spin up the terminal, this, and yeah. Okay. So far, I hope you guys can see both the terminal as well as the VM. Yeah, check the chat. Can you see the terminal and the VM? Okay, right. So let me. All right. So what I'm going to do is I'm going to show you right off the bat. I'm going to show you the output so that we don't miss it like we missed it last time. So the first thing I'm going to do is just for our convenience sake, I'm going to apply a breakpoint. So in order to apply a breakpoint, I can say B, which is break at kernel main. And I'll show you what this kernel main is. This is a symbol. So you might have heard, you recollect in some of these previous sessions, I talked about symbol tables and symbols being very important, etc. Now this is one of them. Kernel main is an actual symbol that's that's present in my simple table. It allows me to directly use it over here. And that's primarily where symbols are really useful. Your code kind of keeps a track of addresses and memory, etc., by actual physical names themselves when you ask it to. Okay, and you could use them as well. So I'm going to hit the breakpoint over here, or sorry, set a breakpoint over here. And as you can see, breakpoint's been set. Breakpoint's been set at this particular address. That's where kernel main is. So now, and I'm going to hit C. C is nothing for what? Continue. That means now that you've set the breakpoint and you've loaded your code, set the breakpoint. Now go ahead and continue. So if I'm going to continue, I'm hitting the breakpoint over here. All right. Now my terminal's already running. I've hit the breakpoint. I can just quickly, just for easiness sake, I'm going to examine what's at this particular address. Now that I'm here, I want to see the next couple of instructions. Right. I can go ahead and do all those things over here. I'll show you a little bit of an involved example, but you can do those things. Let's say I just want to continue again from here. That's it. Once I continue, now you see on the right hand side, I've got my output, right? Let me just show you that output very clearly. So I hope you can see the output now. Yes, can everyone see the output? You should be able to see some output on the warp terminal that I'm using. Are you able to see it? Right. So you see the fact that, we've basically, you see the timer, It says booting on i.MX8 Nano EVK, current privilege level is EL3, the exception handling state, the drivers that have been loaded, all of that. I presume you can see all of that, right? Okay. Question I had. You can only see minicom-b, right? So that's a problem because something is going wrong with my terminal. Let me set it. I had this problem earlier as well. I didn't know. Minute. Okay, that should be sorted out. Now, can you see the window? That should probably be clearer now. I don't know why this keeps happening. Some content shows up, some content doesn't show up. Sort of have to reset it. Anyway, since you guys didn't see it, let me just sort of walk you through that again. So I'll just stop this here. I'll go ahead and load my code again. And I've already set the breakpoint, so I should probably hit the breakpoint again. I'm at the breakpoint again. Now, when I go ahead and hit continue, I should get the same output again, right? So, yes, you guys must have seen that now. Yeah, cool. So that's pretty much the UART working on the i.MX8-A Nano, which is, we're done. It's working now. Now, I'll sort of walk you through a little bit of all the things that, you know, we missed in the last time and why it wasn't working and now why it's working. Apart from, you know, the VM issues that we had the last time, we'll look at the fact that, you know, the pieces that needed to fall in place for the whole thing to work, right? Makes sense. Any questions on this? It should be fairly straightforward, right? Because we've sort of been walking through the whole thing step by step. Yeah. Guess not. So let me show you what the main file looks like. So if you see here, we are basically in kernel main. You saw that I set a breakpoint at kernel main. This is exactly where we're going to be stopping. And the reason I was able to directly say break kernel main and I didn't have to figure out some, you know, some name that the compiler could have assigned, etc., is because that is why this no mangle macro is added. What it does is basically says that, you know, when the code is being compiled, it tells the compiler that, you know, don't play around with this name because I'm probably going to be use it for debugging or other purposes. So keep the name as is. That's exactly what happens, which is why we're able to easily use it to debug or code. And then all of these different print statements are what we're printing out over here. So we print out the version numbers first, what the version number and the package version number is. Then we print out the board, or the type of board that we're going to be booting on. Then the exception handling level that we are at. We're at EL3. If you remember in the last session, I said there are 4 exception levels. Yeah, EL0, EL1, EL2, and EL3. EL3 is the highest privilege level, and we are actually executing at that level. That's pretty much where UBoot or UBoot SPL also runs, which is where we are also running. And then we also have exception handling setup. So we just print some metrics as it relates to exception handling. And then we print out the drivers that we've just loaded. In this case, the one driver that we've loaded is the UART driver. And then the last one is we print out how many characters have we printed. This 388 correct, from here all the way till here we've printed 388. Okay, now this 259 was some debugging step that I was doing, but I've commented that out since. Okay, so up to this point, any questions? No questions. All right, great. So that makes sense, right? We've sort of went ahead and enabled, written some startup code, written the linker script, written the main, main.rs file, and we're done. Here is where, you can start looking at other pieces, which is when you start seeing this, let's say I want to see a couple of things. So when I hit BT, you will see that when I hit BT, you'll be able to see that the entire backtrace, that means all of the different stack frames or all of the different function calls that have happened so far since the program started, or since my bootloader started, should all be visible to you now. So right now we're in this wake from events, but even before that, we started out in Rust, which is, I'll just show you how we show you the flow of things. If you go to boot.rs is where, start_rust is the first function that's called. Then we do a lot of initialization within it, a lot of setup, and then we jump to kernel init. And once we jump to kernel init, you will see that, we further go ahead and load the driver. And once that driver is loaded, then we have kernel main. We jump to kernel main, and in kernel main, we jump to the last method, which is wait forever, right? Now let's go look at the backtrace that we just saw with OpenOCD. You'd be able to see that that's exactly what happens. Start Rust, kernel init, kernel main, and then wait forever. Further, if you drill down a little more, you'll find that wait forever is actually calling something called WFE, which is wake for. All right, so that's pretty much, in a nutshell, how debugging works when you're using something like a JTAG debugger, right? Okay, this is all the happy stuff. This is all of it when it's working, right? When everything is working, this is what you get. We'll try and take a look at one piece of, one part of this puzzle that wasn't working and how I was able to fix it. We'll take a look at that. But before we get there, any questions on this so far? Oh, sorry. No questions, right? Good. Okay, cool. So we've got everything working now. I just showed you the, the backtrace as well. So we're good. Now, the last part that I wanted to cover today was to actually talk to you about what are the pieces that I added to make all of this work. So the first thing that I wanted to sort of walk you through is, let me actually pull up, close the board. Let me close the bootloader piece just for now. let me pull up the HAL, hardware abstraction layer. In the hardware abstraction layer, there's just like 3 things that I've added, which is what I've mentioned here, which is counters, clocks, and muxing, right? So let me start with counters. The reason I needed a counter to enable the counter is primarily because of logging. Means you see all these, see the value 30 point whatever, 258 point whatever, all of that. In order to get that, timestamp as such, I needed to turn on the counter. Counter is basically something that counts upwards using a certain frequency, and we just basically enable the system counter itself. But in order to enable the system counter on or any other peripheral that uses any kind of clock on the i.MX8 board, you actually need to enable those clocks, or rather the right word that they're using is called ungate those clocks. So there's some clock gating involved, which is what we did not consider that exists. So in terms of clock gating, what I've done is I've basically said, okay, create another module in your BSP and call it clocks. And this is the module that has been implemented, which is the clock control module. Now I'm not going to dive very quickly deep into this because it'll take a little while, but I've put in the documentation, so it's pretty simple and easy to understand. Effectively, what we do is we need to do 2 things. We need to go ahead and basically enable or disable the clock gate first. For, let's say you've got a peripheral like UART2. It's using, technically UARTs don't have a clock, but for some reason in the i.MX8 board, they do use a clock. At least they need a clock. They don't use it because UART is an asynchronous protocol. It doesn't really have a clock. But anyway, in this case, it needs a clock. So you first need to enable that. That means allow the clock. And then you need to specifically enable it. So those 2 steps, once you do that, you're good. And that entire implementation is inside the clock section. Then the other one is muxing. So muxing is what we call pin multiplexing. You've probably, worked with this in your Cortex-M sessions. Effectively, what's happening here is the 2 pins that come out of the SoC and connect to, for example, let me pull up that image again. Yeah. So if you see this is the JTAG port, right? And then, yeah, sorry. This, I hope everybody can see this. Everybody see this? That. Yeah, everybody can see this picture. I've just zoomed into the bottom left. This, you should see that this is the micro USB connection. This micro USB is connected to another serial to USB converter, which is directly baked on the board. And that is what's connected to the UART2 port. Okay. Now, in the i.MX world, because the number of pins that come out of the SoC are limited, you might want to reuse the pin for other functions. So the same pins can be used for other things. And that's what muxing is you're going to define the function of that pin currently. And we needed to do that as well. And so I went ahead and pretty much wrote those parts as well to say, okay, go ahead and set the muxing values for the UART2, which is what you see here. Right? So we set the muxing value. We set the muxing configuration for the UART2. Once that is done, and once we've set the clock and the counter, now we're in a position to go ahead and start printing. All right. So this is so all of this stuff is not common for all boards. It's specific to specific boards. In this case, it's specific to the i.MX8 and its architecture. Okay. Right. I hope that makes sense. This is fairly straightforward. I'm not doing much over here in both cases, in the clocks case and in the muxing case. All I'm doing over here is at the end of it, I simply write to a bunch of registers, a bunch of values, and I have to do them correctly. That, you know. And if you were to look at the initialization section that I have, is when I'm starting Rust, I do all of these things over there. I set up exception handling, I enable the UART clock, then I enable the counter, I start the counter, set up the muxing configuration for the UART2, then I jump. Once I do all of these things, only then do I jump into kernel init and start loading my driver and continue with my things. Any questions on this part? Right? Going once, going twice. Any questions? And then cool. All right, so now let's actually jump into a little bit of an interesting part, because there was many problems that I solved along the way. One is obviously you saw that the disabling of the MMU during the debug stage, because that was an issue that went on for a while. Then there were other issues to do with this clock gating and stuff. So lots of things that we need to actually figure out. I'm actually going to pick one of them so that, you know, you have an idea about how to think of things. Did you face initially any issue for clock setting? Yes. One is without setting the clocks, that is without gating or ungating the clocks. If you were to, for example, that's what I'm going to show you. If whenever I implemented my UART driver, and once the driver was implemented, I was trying to basically set up the UART. So one is I initialize the UART, and then I start using the UART to print out my data, right? What my logs are. But I was never able to, because I did not gate the clocks, I was never able to write to the registers. Whenever I used to write to the memory mapped registers for the UART, nothing used to happen. When I looked at the assembly code, everything is working. Everything is written properly, but none of the writes actually take effect. They're all ignored. Right? So that's one case. And in order to figure that out, diving through the reference manual was the only option, right? Basically going through it and saying, okay, you have to go ahead and enable the clocks before you can actually use the UART. And that was a bit of a headache, because UARTs don't have a clock. Why am I being forced to enable some clock? It's just the architectural thing that they've got going. And yeah, that's it. So while we're there, let me sort of jump into that. Let me show you an example of what I mean. Okay, so let's say I load my, I load my code again, and this time I'm going to show you all the breakpoints I've got. So I've only got one breakpoint, which is so if I do info B, give me information on all breakpoints, I get to see all the breakpoints. So I'm just going to delete all the breakpoints just so that, we start off clean. I've just deleted all the breakpoints. Now, the first thing that I want to do is I wanted to show you, I want to actually break on something called init UART. Okay, because the reason is that's exactly why, let me show you why I'm easily able to call it init UART and just jump to that point. Firstly, let me go pull up my driver, my UART driver. This is my UART driver. It's rather lengthy, but don't worry about the length, because most of it is just one macro, which is bit fields. I first have to clearly specify all the bits for all the registers that I'm going to be using. Anyway, once that is done, here is where I initialize my UART. And see, again, lo and behold, no mangle. Without this, it would have been very difficult for me to actually set a breakpoint over here, because I have to step through each instruction, find the exact one, and then I'll end up in the right place. Now that, you know, I've set the no mangle over here, I can simply go ahead and set my breakpoint. Sorry, where's that? I can simply go ahead and set my breakpoint like I do with init UART. Okay, so that's where's that? Yeah. So init UART over here from my code in the IDE. Now in my book, in the VM, when I'm trying to debug, I'm also going to set the same breakpoint. Happen. Not defined. Oh, maybe I didn't compile it like this. But okay, generally this shouldn't be a problem. You should be able to directly start off from here. So now that that's not possible, let's see. Now let me show you how the hoops that we have to jump through to get this point. So where does UART get actually initialized for me? If I go into my main code, the first place where this actually gets initialized is over here. That means in the kernel init section, that's where I'm doing my driver loading and initialization, right? So I'm actually doing it over here, which is, you know, if I was to reference it, you'd be able to see. This is where, oh, I moved the no mangle. Possibly. Anyway, so I need to go ahead and sort of jump to this point and get to a place where I can say, okay, this is init UART. The other way that I can actually do this is I can go ahead and look at the symbol table. In order for me to look at the symbol table, I'm just going to go ahead and do okay, then I'm basically going to say, okay, so if I'm just going to go ahead and run this, so instead of me looking through, you know, every place for the simple tables, etc., all of the symbols are actually present here. This is what you need to, you know, this is why things like object dump and all of those utilities, which we haven't used to a large extent, that's how they are useful. I'm able to actually go ahead and dump a lot of information. One is obviously I'm going to be able to dump a lot of the basically the layout of my code, the text section, the read-only data, global offset, all of that stuff. All of those sections are clearly laid out over here, and their load addresses as well as offsets are all set out over here. I mean, that's not important right now, but in any case, you'll see that all of the symbols are present in my symbol table because we have a very tiny program and we've ensured that some of the symbols are no mangle. Here's what happens if you actually mangle it, right? If you don't say no mangle, this is what the compiler assigns to the name of your, you know, function or whatever, the symbol that you are looking for. And that can be really, really irritating for you when you're trying to debug because you can't find the right, you know, thing. Okay. So one of the ways to do this is, look, init is available. So init was, I remember this was where I put up a no mangle symbol. So I'll probably go ahead and just sort of use that. Let me simply jump to back here and say, see, so instead of me going to go through each instruction and figure out where I should put a breakpoint, now I'm simply going to go ahead and do b-init, and you see I directly have a breakpoint inside the UART file. Make sense? Any questions on this? UART implementation was not seen. You guys can see the VM and the VS code that I was just walking back and forth. I was just walking through the VS code instance. Were you able to see all of that? The glitches to. Yeah. So Yashwant, to your point, to your question, the UART implementation, I just walked through it. Were you able to see it? The UART implementation is right here. Oh, okay. Again, I need to restart. Okay. Just pull this up. Okay. Now you should be able to see it. Sorry, for some reason, all the applications were like stuck. Restart every single one of them. Okay. Now I think you should be able to see the UART implementation. Okay, perfect. So this is the UART implementation. And as you can see in the UART, init UART, there's no mangle. So I was trying to actually find out, a breakpoint over there, but I couldn't. So now I just went ahead and did b-init. I'm able to find it. The reason I'm able to find it because I have to recompile it, which I have not done. So anyway, I don't have time for that. I went ahead and set a breakpoint on b-init, and now I have a breakpoint set up. So if I do info b, you will see that we have a breakpoint in the UART 0.rs file. Okay, so far so good. We're just going to debug this particular implementation. I just wanted to show you what that looks like when you're actually debugging your code in using something like a hardware debugger or a JTAG debugger using OpenOCD. I wanted to show you that as the last piece. So let's go ahead and continue. Run the code right now. So now I've ended up here. Once I basically continue, I've ended up at the breakpoint. So you can basically look at the, what do you call the program counter, or the instruction, where the instruction pointer is. You will see that the instruction pointer is right here. It's at 9160D4. I can actually do a little better than that. I can go ahead and do X, which is X is for examine, I is for info. So examine the next 10 instructions from where the instruction counter is. That's what I'm doing right now. And you should be able to see that, okay, I'm inside this particular function called init. Okay, and inside init, I have a whole bunch of things that I'm doing over here, right? I'm doing some store, some load, some branch, if not 0. Again, I'm doing a load, etc. Is that clearly visible? Let me show, sort of make this a little smaller. Yeah, I just made it a little smaller. Is that still good? Okay. So these are the instructions, but this is an important piece, because the way you can go about debugging this is, when I was stuck over here, is first I would like to see what, because I wanted to know whether or not, see, I'm doing all these things over here, right? I'm doing registers set 0. That means set this register UART2 UCR1 to 0, UCR2 to 0, and then go ahead and check something. Then set this to 84, set this to hex 8000, right? I'm trying to do all these things. I want to see if those writes are actually happening in in memory, if those writes are actually happening. The UART peripheral is located at x30890000, right? That's where it's located. I want to see whether that's actually happening over there, right? So the first thing I see is, I'm going to go ahead and say, let me actually look at a couple of things here. So let me just print out all the registers that I can see right now. So here's me printing out the entire set of registers. And you will notice something, that X8, register X8, contains the address 30890000. This is essentially my memory mapped address for my register, which is my UART, all right? And if you were to look at this instruction, it's saying that add 80 to X8 and store 0 in it, right? That looks exactly like this instruction, right? Like line 897, where we are basically disabling the UART. That's exactly this one line. Same thing again when we try to do UCR2, which is, because there's only 4 bytes of difference between UCR1 and UCR2. UCR2 is it's at hex 80. This is at hex 84. That's exactly what's happening here again. And then if you look at the next one, which is load W9X8132, which is, we are trying to load a value in. So we were trying to, firstly we were trying to set 0. That means write to it. Now we're trying to load into it, because we are trying to do a while loop check over here, right? Same thing, same UCR2. That's why the addresses are the same here and here. Does that make sense? Sort of? Yeah. Questions on that? Okay, perfect. So now if you just follow that, so this second part is the loop part. It says, if you test it and if it's 0, go ahead and go back to jump to this part, right? If it's not 0, if it is 0, keep looping, basically. That's sort of what we'll keep doing. Now, the other part is, this one is a no op instruction, which means nothing happens. You just go through. Then the next one is basically, it's the same thing over here again. You basically load it over here and check to see whether you want to go back to 0 or you want to come back here. So this is basically the loop that we see in that is from lines 901 till 907, and the no op that I explicitly put over here is being translated over here. Okay, anyway, this is the loop. Now, once you're out of the loop, the next piece that you want is, you see this 84? We've got this 84 over here. You want to set that to UCR3, right? And so anyway, it's UCR3 is not showing up here. So if I want us to show up, I basically go a little more. I say, show me 15 instructions, right? So if I have to see 15 instructions now, you will see that I'm going to be moving the value 84 into W9. And then I'm going to be moving 8000 into W10. And then I'm going to be moving X2B into W11. And then somewhere I'm going to start moving all of these things in, right? So store whatever W9 in is it, whatever's in W9, store it in X8 136. Whatever's in W10, store in X8 plus 140. Similarly, we're going to do all of those things, which is what I've got going here, right? Make sense? So this is what we would do in order to step by step go through instructions, see that, you know, whatever you're doing is exactly working correctly. This way I was able to figure out, you know, there was an ordering issue. That means I had to do one operation before the other. That was fixed when I went through each, you know, instruction by instruction. And if you notice something very important here is, it's not, you know, each statement is not taking like a bunch of different instructions. The way Rust is being compiled, the compiler is compiling, it's doing a really good job. Everything is just one instruction. In fact, that's how it should be. This is basically Rust. And the fact that you are basically doing register writes, there's no reason for it to be more than one, right? Okay, any questions on this part? Because I think we've sort of come to the end and we've again overshot by, but kind of cool. We've sort of solved the first part of the problem, which is to get the UART up and running and also to get the different pieces in place. So we've got a good board support package right now, a very minimal one, but it's good enough. We can now start building things like the eMMC driver. We could build a bunch of other drivers, and then we can also build the secure boot hab API that we need for the i.MX. All of these things can now be done. The basic pieces anyway in. Any questions on this part? And have we covered everything? Demo as well. Right. Any questions? Okay. Cool. All right. Since there are no questions, that's about part 2 of the board bring up series. We're sort of done with board bring up. Next, I think in the next session we can, if we do this or if we do something else, if we do this, maybe we'll talk about other things, like bringing up drivers that are more critical. All right. Yes, we are able to, you know, go ahead and boot, because I think we just saw that here with when we did something like BT, we're able to get a good safe backtrace. We're able to go ahead and actually look at every single call that we're making, etc. So all of that is good. We're also able to print out fully, which means we just saw that when we did this print one, but we saw that, you know, we're able to print exactly what we needed to, right? Make sense? Okay. All right, guys, that's it. That's it for this stream. The next one, we'll look at something a little different, maybe. We'll actually, you know what? We'll actually come up with like a list of topics and choose from, and then we can do doing streams. Be interesting. But yeah, maybe we'll talk about that. All right, that's it. Have a good day. Bye.